Hello, and welcome to the last lab of the semester for Physics 220. And it's been a rough semester, but let's finish it off strong. What today's lab is going to address is fluids. Now, you're not going to see the content that appears on this lab on the final exam because it's sort of done. It's done so close to the end. I want you to see it, but you will not be tested on it. However, there are problems on the bonus homework if you choose to do it that involve fluids, and you do need to do the lab for credit for the lab class portion of the class. So you'll learn something about fluids by doing this. And today the topics will be, there'll be two topics we're going to discuss about fluids. One is going to be the pressure inside a fluid. And as you know, if you've ever gone scuba diving or swimming, the deeper you go in the water, the higher the pressure is. And we're going to talk about that. It's because of the weight of the water that's on top of you, effectively. And I'll do a little calculation with that, and then we'll make some measurements, and you'll get to see a little bit about pressure. After that, we're going to work on how to use a very interesting principle called Archimedes' principle to determine the density of an object. And that is going to involve a new force we're going to see called the buoyancy force. And you'll see more on the buoyancy force and on calculating density on the second half of the lab. All right, first part is going to be on pressure in a fluid. My discussion of pressure is going to begin with the equation that the pressure that we associate with anything when we think of the term pressure, it's equal to the force that something experiences divided by the area over which that force is acting. So the units of pressure are going to be newtons per meter squared. That's the SI unit of pressure. That has another name. It's often called the Pascal. That's the unit of pressure, or PA. So when you see a PA, you'll know that that's a unit of pressure. Now, a Pascal is not a lot of pressure. When you think about it, a Newton is not a lot of a Newton is not a lot of force, and a square meter is a pretty big area. So this amount of pressure is not really that much. Compared to the pressure of the atmosphere over our heads, 1 Newton per square meter, 1 Pascal, is a tiny amount of pressure. We'll talk about that. The atmosphere is actually about 100,000 pascals. It's about the sea level pressure that we're experiencing right now. Let's think about pressure in water. So when you have water, it's like this. Say you have water that has a certain depth of water here. And I'll call that depth H. I'll just call it H, like a height of water. And I'm going to look at what is the pressure as you go deeper in the water. I'm going to ignore the pressure of the atmosphere up here. I'm just going to consider the pressure of the water itself on a certain area down here. Let's say you have an area. It could be a square, it could be a circle, but it is something that has area A. What would be the pressure when you're at some depth here? Actually, I'll make the depth be down this far, so I'll make my area A be there. All right, so that I'm under a depth H of water, and I have an area A. Well, remember what I told you, pressure is equal to the force divided by the area. The force is equal to the weight of whatever's above that object of area A. So I'm going to imagine here that we have kind of a tube of water, or a cylinder of water, or a rectangular prism of water. Doesn't really matter what the shape is, other than it's going to be a symmetric shape in the depth here. It's going to have the same dimensions here as it does there. It's not going to be any wider there than it is there. So I'm going to say that the area above that, or the volume of water above that area A, is going to be equal to the density of the water. Remember, the density is the number of kilograms per cubic meter of water. That's the density. And it's density of water. So I'll put a little W there so you know it's the density of water, times the depth, times the area. Note that that is the volume. The depth times the area is going to be the volume of this region here, because it's a three-dimensional region. You're only seeing it in 2D here, but it actually has some thickness that way to it, and the area gets at that. So the area is in square meters, the depth is in meters, so that's cubic meters, which is a volume. Density times volume is going to give you mass, because remember, the density is the amount of mass per unit volume. Multiply that times volume, and you're back to mass. So this here is like the mass. So if I want to know what the weight of the water is, I shouldn't say this is V, this is M. V is this. So this whole thing is the mass. I want to take the mass times gravity, and that's going to give me the weight of the water, if you remember. That's going to give me the weight. So what I want to do to get the weight is I'm going to take mass times gravity, and that's, in order to get that, I'm going to find the mass, which is the density of the water, times H times A times G. That is going to give me the mass of the water, the weight of the water that's on top of me. The mass is this part, times G gives me the weight. All right, and that's going to also be in newtons. All right, so I'm going to now take that and calculate the pressure. I'm going to know that this is the force. I'm going to have to divide it by the area, and let's see what the pressure is as we get deeper and deeper. So this is the equation. I just moved it to another fresh sheet of paper. And remember, the pressure is going to be equal to the force that an object experiences, which in this case is going to be the weight of the water that's on top of it, divided by the area of that object. So what I'm going to do is I'm going to take the weight, and that's going to be equal to that expression I have there, the density of the water times A times H times G, and I'm going to divide it by the area. And you should see, oh my gosh, there's two A's there. Those two A's are going to cancel each other out. So I'm going to be left with the pressure in water at some depth H is going to be equal to the density of the water times H times G. That's going to be what the pressure of the water in pascals is going to be. It's a function of depth. Depth is this. And G, of course, is the 10 meters per second squared, or 9.8 meters per second squared. The density of water is typically given in kilograms per cubic meter, or in grams per cubic centimeter. But since we're working in SI units here, and this is in meters, and this is in meters per second squared, it makes more sense perhaps to have the density in units of kilograms per cubic meter. And so it's a useful thing to remember. You might remember the density of water in grams per cubic centimeter is 1. It's 1 gram per cubic centimeter. If you scale that up and figure out how many kilograms per cubic meter that would be, I'll leave that exercise to you. But the density of water in kilograms per cubic meter is 1,000. And we did talk about this right at the beginning of the semester, ironically, maybe the first day. If you have a cubic meter of water, it weighs a metric ton, which is 1,000 kilograms. Remember, a cubic meter is pretty big, but still, that seems like a lot. Well, water's pretty dense stuff. It's pretty dense stuff. There's denser things, as we'll soon see, but a cubic meter of water is a fair bit of it, and there's 1,000 kilograms of mass of water in that cubic meter. All right, so this is our expression for pressure, and this is the pressure that's just due to the water. And I'm going to take this from there, and we're going to we can consider the atmosphere on top of the water and add that in too. So now I want to consider what might happen if you have atmospheric pressure on top of the water, which is what we have. When you're on top of the water, it's not like there's zero pressure on you. You still have atmospheric pressure on you. Of course, as you go down, you have the atmospheric pressure plus the pressure of the water that is going to increase as you get deeper and deeper. So that actually gives us rise to two definitions for pressure. One is the gauge pressure, and that's the pressure that we just calculated, which is associated with just the water itself. It's the density of the water times the gravity, G 9.8 meters per second squared, times the depth in meters that you're in the water. There's also something called the absolute pressure, which includes the effect of the atmosphere. So if you're at some depth here, not only do you need to include the pressure associated with the water on top of you, but you also have to add into it the pressure of the atmosphere, which I'm going to call P0 right there. Now the atmospheric pressure varies. In fair weather, it's higher pressure, and when you have rain and storms, that's when you have a low pressure region. The center of a hurricane is typically extremely low pressure. So pressure plays a big role in what kind of weather we have going on, and you'll learn more about that in a different class. What I will say, though, is that typical sea level pressure on the average is about 100,000 pascals. It's actually 101,000 pascals, which is a fair number of these pascals. But when you remember that a pascal is only a Newton per meter squared, it takes a lot of them to equal an atmosphere. which is the weight of all the water, the weight of all the air over your head. That's what's causing the atmospheric pressure. One thing that is useful to think, just kind of a rule of thumb, is how deep do you have to go in water to get an atmosphere of pressure? You might imagine you don't have to go very far because water is much denser than air. So if you go down a certain distance, how far do you go down until you have an atmosphere of just water pressure above your head plus the pressure of the atmosphere itself? In other words, when is the gauge pressure equal to 1 atmosphere at what depth? And I'll take this to be fresh water, and salt water it'll be at a slightly lesser depth because salt water is a greater density than fresh water because of the salt in it. But for fresh water, I can say that, let's just take a look here. If we want the gauge pressure of fresh water to be 1.01 times 10 to the 5th pascals, let's set that equal to the density of water times G times H. And let's calculate at what depth you're going to have that pressure. So here all we have to do is solve for H. So we divide 1.01 times 10 to the 5th pascals by the density of water and by G, and that should be the depth at which we'll experience 1 atmosphere of pressure. Go to the next page and do that. So let's see. I have 1.01 times 10 to the 5th divided by the density of water times G. That is going to equal the depth at which you're going to experience 1 atmosphere of pressure just due to the water itself. So I take 1.01 times 10 to the 5th divided by the density of water. I'm going to take pure water, 1,000 kilograms per cubic meter, and I'll go with 9.8 meters per second squared here. I'm going to have to use my calculator in either case. And do the math, and let's see what you get. All right, hopefully you did the math and you got 10.3 meters as the depth of water, pure water, at which you'll have 1 atmosphere of pressure. What I'm going to do now is I'm going to use a pressure sensor, which is this. It's a vernier device. I can attach it to the Logger Pro, and at the end of this tube here, I can dip it in water, or I can do other things to it to make its pressure change. And we can record what that is. And that'll be what I'm going to do for this part of the lab. But before that, I normally bring a syringe that I can squeeze on this and increase the pressure to be a few atmospheres, or to create a partial vacuum, and I can decrease the pressure to be just very close to 0. I'm going to try doing it since I don't have the syringe with me. I'm just going to blow into the tube to try to increase the pressure. I won't get 2 atmospheres. I might get 1.2 atmospheres right now. So notice that the pressure is in atmospheres. I'm going to change that just so you see I can change the units of pressure. I'll make the pressure be, rather than atmospheres, which it's about 1, which makes sense. I'm at about 1 atmosphere right now. I'm sitting here at sea level or close to it. But what I'm going to do is I'm going to change the units, and that's under data, I believe. Let me see, where is it? Here it is, under experiment, change units. Instead of having units of atmospheres, I'm going to go with units of kilopascals. That means 1,000 pascals. Remember I said that 1 atmosphere is about 1.01 times 10 to the 5th pascals, or it's about 101 kilopascals, which you can see is the value right there. So you can see it better, I'm going to press collect. Let's see, I think you can see that now. Couldn't see that a minute ago, I apologize. But you'll be able to see it now. All right, I think you can see that. We're at about 101 kilopascals, which if I made this atmospheres, as I said, was about 1 atmosphere. What I'm going to do now is I'm going to breathe. I'm going to force air into this. I'm going to blow out, and we'll see how much pressure I can get in here. I couldn't even quite get to 120 kilopascals. Now I'm going to suck like it's a straw, and let's see how low I can get the pressure. It will not become a vacuum. It'll be maybe 80 kilopascals if I'm lucky. Let's see what I can do. That's pretty good. I got it down to 40 kilopascals. So I could actually make it lower by about 60 kilopascals and make it higher by about 20 by either sucking or blowing on the straw here. All right. So hopefully you can see that that's how I can measure pressure. Next thing I'm going to do is I'm going to dip this into a large beaker that you're going to see, and we're going to see how the pressure changes as I get deeper and deeper into the beaker. All right, now what you're going to see me do is I'm going to be dipping the meter stick with the tube on the end of it into the water, and this beaker goes down. It's about, you can't see the bottom of it, I know, but it's about 59 centimeters deep. I can't quite get to a whole meter, but I'll be able to see an increase in pressure, not a whole atmosphere, but at least a fraction of an atmosphere, and we'll be able to measure that and take a look at that in Logger Pro. So I'm going to let you see Logger Pro while I'm doing this. And what I'm going to do before I put the hose in is I'm going to zero it so that, well, I'll start by zeroing it right now. So now atmospheric pressure is 0. So I'm actually measuring the gauge pressure rather than the absolute pressure. So I wanted to do that. And I know I'm not going to get to a whole atmosphere. And an atmosphere is about 101 kilopascals. So I'm going to stretch this up a ways. So I'll make the maximum here, rather than being 200, which is like 2 atmospheres, I'll make it, let's say, 1/10 of an atmosphere. All right, so I'm going to be starting at 0 when I press collect, and it's going to go for a good long time, which is great. I have it going for like 800 seconds, which is more than enough. All right, here goes, and press collect. And right now I should be pretty darn close to 0. Indeed I am. And I'll read you the depth as I move it down, and you can record the data as the pressure changes at different depths. So at 0 depth, it's that. I'm now at 10 centimeters depth. You can see the pressure went up to about 0.85 kilopascals. 20 centimeters depth, 1.70 kilopascals. 30 centimeters depth, 2.55 kilopascals. 40 centimeters depth, 3.40 kilopascals. 50 centimeters depth, 4.25 kilopascals. And I can't quite make it to 60. It's actually, looks like 56 centimeters depth is the deepest I can go with this. 56 centimeter, 4.76 kilopascals. All right, I'll pull this back out. You'll see the pressure go back down on the graph there, as you would expect. And that's your data for most of this lab, or for most of the first part of the lab. The only other thing I'm going to do is I'm going to put the same water that's in here into a flask that has a slightly different shape. And I'm going to ask you a question, and we're going to test the pressure in the flask and see if it's any different as I go deeper and deeper. This is a pretty fun part of the lab, and what I like to do is ask, this is a flask that I'm going to pour this water in, and if this were a class, I would say, well, I have too much water or not enough. This is the beaker, it's almost full. How much will it fill up the flask? Will it overfill it? Will it underfill it? Will it be just about right? Glancing at it, what do you think? Now I'm going to do it. To try to minimize spilling, I'm going to put the flask in here. Of course, you can't see if I'm spilling around it, but you're just going to have to trust me. I'm going to have to trust me. This is kind of hard. Spilling very little. My garage, I don't want to have a flood in here. Enough problems. Here it comes. Let's see. Look at that. Wow. It just filled it up completely. It's going to spill out a little bit now when I stick the meter stick in, but literally what was in there just filled that. So they're pretty much the same volume, which sometimes surprises people. It's kind of fun. Okay, I'm going to repeat exactly what I did last time. I'm going to be dipping this in here. You're going to look at the pressure as a function of depth. So right now we're at depth of 0. The pressure should be close to 0. It's something a little negative, but that's okay. Very close to 0. We go down 10 centimeters. And I'm going to go down 20 centimeters. You're just going to have to look at the numbers yourself. I'm busy focusing on this. You compare them to the other numbers. Here's 20 right there. 30 centimeters. That's about as deep as I'm going to be able to go. Slightly more than 30, but 30 centimeters. With a little bit more, I can make it to about 35.5 centimeters. That's the deepest I can go right here. My question to you is, this is directly below. What do you think is going to happen to the pressure if I happen to put the meter stick at the end of the flask there? Would you say maybe it's less pressure because it's kind of less deep to get from here to the glass wall? Or is it going to be less pressure or more pressure than it is now? What do you think is going to be the case? Well, I can try it. I'm going to move the meter stick over a little bit. Right now where it looks like at about 3.0 kilopascal. It's going to vary by a few hundredths, and 3.0, 3.06. Let's see what happens when I go over to here. Looks like it's still about 3.06. Go to the other side. Is there any difference over there? I'm still saying 3.06 kilopascals. So I'm not seeing any change in pressure as I put it at different points here, but it's all the same depth down here as it was in the middle. So pressure is just a function of depth. It's not a function of the horizontal position. That's my point of this activity. All right? It's one of my points. All right, you have all the data you need for this part of the lab. Next part is Archimedes' principle.